I will begin. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you'd guide our work today, Lord, and help us to, again, Lord, just to glorify you in what we do, Lord. In your name I pray. Amen. All right, so at this point I've lost count of which lecture we're on. I estimate 31. Not sure. But in any event, I'm still in lecture 26 of my last year's notes, which is 4.1, the end maybe, 4.2 in Nicholson. And this is my corollary, 3.4.10, which I thought would be a good thing to start with today, which says f is a field, A in the field, f of x, polynomial over the field, all right? Then f of a is the remainder. In division of f of x by x minus a. All right. Okay, so is that me? I thought I heard a beep. What was that beep? No? Okay. So the proof, this marker has not long to live, applied to the division algorithm, right? So that implies that there exists what? There exists Q and R such that f of x equals to x minus a times Q plus R, right? So here I'm applying the division algorithm to f of x divided by x minus a, essentially, right? And what does it give me? Then here, either what? R is equal to 0, or what is the other? Or the degree of R is what? It's less than the degree of the thing we're dividing by, right? Which in this case is what? 1. Right. So, right, in other words, the degree of R has to be equal to 0. So thus, R is a constant, right? And hence, if you calculate f of a, what do you get? So this is 0, right? And so we get R. There you go. This is sometimes called the remainder theorem, right? Corollary to that, f of field, all right, f of x, polynomial over the field, all right, then a is a 0 of f of x, if and only if what? X minus a is a factor of f of x. Now, what you said, Alan, is not wrong, but that's the definition of a 0. So what this means is that f of a is equal to 0. Right? We defined that a is a 0 if when you calculate the evaluation homomorphism acting on f of x, right? When you feed f of x to the evaluation homomorphism, you get 0. Then it's a 0. Okay, so I won't even prove this, but the proof, well, I mean, I don't know, I guess we could prove it. It wouldn't take us long, would it? How would you prove this?
You just use the corollary because it is a factor and the remainder is 0.
Right, so the forward direction, if f of a is equal to 0, then f of x is equal to what? X minus a times the q, right? Plus 0, just to write it down, I mean, which is to say x minus a is factor, right, of f of x. And how about the other direction? The other direction is even stupider, right? If you have f of x is equal to x minus a, right, times g. I'm sorry, I seem to have, I told you guys I would do this. I would have my cake and eat it too. See, here I'm writing f of x on the one side, and then I'm writing just g over here to be equally. There we go. Or you could add x both sides. Whatever. Anyway, let's be symmetric in our abuse of notation. And so, anyway, point being that f of a is what? It's a minus a. Here I'm using the evaluation theorem, right? Which said that the evaluation map is a homomorphism. So I just, what that means, of course, is what we already know, which is we plug in a wherever x is, or to the appropriate power. And of course, that gives you 0, right? Which is to say that a is a 0. So if x minus a is a factor, f of a is 0. If and only if. It is important here, of course, that f is a field, right? All right, corollary, that was corollary 3.4.12 in my notes. All right, the next one, which I will state for you guys, corollary 3.4.14, and it states the following: if f of x is a polynomial of degree n over f, right, a field, then f of x has at most n distinct zeros. So I have a constructive proof in the notes, but I'm going to give you a proof by contradiction here because I think it's easier. And here's the proof. Suppose otherwise. It's pretty easy, right? Suppose f has more than n zeros. Say a1, a2, a3, dot, 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 am, where m is greater than n, right? Then all you do is apply the corollary 3.4.12 m times, right? I repeatedly apply the previous corollary. What's that give me? So we get x minus a1, right? X minus a2, and so forth and so on. X minus am times some polynomial g, right? Let's repeatedly apply the corollary. But what then do I have? This implies that the degree of f, right, is greater than n. Well, in fact, it's greater than m, right? Well, it's greater than or equal to m, I suppose, which is by assumption greater than n. But that's impossible, right? Because the degree of f is n. So that's a contradiction.
And that's because we're a field, so we don't have any 0 divided. Oh, I guess.
Right.
Multiplying 1 by 1.
It's because we're over a field. Although in the little video I posted earlier today, I prove in there, or sketch the proof in there, that the degree formula works in a domain. In other words, if we have f and g over a domain, then the degree of fg is the degree of f plus the degree of g. Certainly it's true for a field, yeah. Now, so that's kind of neat. And it's sometimes useful. I like this example. So let's look at f of x equals to x to the n minus 1. This is, of course, a polynomial over the complexes, right? And you can see that omega equal to the exponential of 2 pi I over n, right? This has omega to the n equals to 1, but omega k not equal to 1 for k equals to 1, 2, 3, n minus 1, right? So, put that together, we have solutions. And of course, it's also clear that omega k to the n is what? This is omega to the n to the k, right? Also, which is 1 to the k, which is 1. So every one of these is also a solution. In total, what are the solutions we have? We have solutions 1, omega squared, omega to the n minus 1 for x to the n minus 1 equals to 0, right? In other words, these are what? You can see that these are zeros of f of x equals to x to the n minus 1. And so we can factor, right? So f of x is equal to x minus 1 times x minus omega times x minus omega squared, x minus omega to the n minus 1. You're probably most familiar with this in the case n equals 2, right? Then we have f of x equals to, x squared minus 1, which is x plus 1 times x minus 1. Kind of boring, right? This gets more exciting when we look at like the third root of unity, right? Or how about let's skip ahead to 4. N equals 4, we get f of x equals x to the 4th minus 1, right? Which is what? Which is x squared plus 1 times x squared minus 1, which is x plus I times x minus I times x plus 1 times x minus 1, corresponding to the fact that 1, I, minus 1, and minus I, these are the fourth roots of unity, right? So, anyway, I think it's an interesting application of the factor theorem, if nothing else. Moving along here. Oh. See, I am going to regret not having this. It's a little bit wet. I was cleaning my my cloth here. It's a little bit damp. All right. So definition, principal ideal domain. What's a principal ideal domain? R is a principal ideal domain, which we like to abbreviate as PID, if every ideal, each ideal I in R has form I equals to A, where of course that has our usual meaning. And here I'm assuming R is commutative. I should probably throw that in there. RA such that R is the ring. Pretty much everything we're doing from this point out assumes R is commutative. All right. So many of our examples are principal ideal domains, but not all. Here's an important one. Excuse me. Goodness gracious. Theorem 3.4.17 says that if F is a field, then polynomials over F are a PID. All right. How do we can prove this? So what do you guys think? How do we start? To prove that the polynomials over F are a field, we start by picking an ideal, right? So we say let I be an ideal of the polynomials over the field, right? If I is 0, if I is the 0 ideal, then we're done, right? If I equals 0, well then 0 is the principal ideal generated by 0, so we're done. Okay. Otherwise, I is not equal to 0, right? Thus, there exist polynomials of I should say there exist non-zero polynomials, right? Non-zero polynomials. Why is that important? Non-zero polynomials of least degree in I. You see, if it's the 0 ideal, then degree is not defined. But if it's non-zero, that means there's at least constants or something more in it. Those have well-defined degree, but degree is non-negative, which means I can apply the well-ordering principle to it. There has to be a polynomial of least degree, because you can look at the set of degrees. That's a set of natural numbers bounded below by 0. So let g of x be such a polynomial. Of least degree in I. Right? And then what should we do? We want to show that I is principal, right? So at this point, I should take something else in I. Let's say f of x, right? And then what can I do? Pretty much the only tool I've got to work with here, theoretically, is what? The division algorithm, right? So f of x is in I can divide by g, right? Thus, there exists q of x and r of x You know what, I'm starting to regret writing of x. You see why we shouldn't write of x? Look at how many extra of x's I've written in this proof alone. Of x, of x, of x, of x. So many. But it's a bad habit I have a hard time getting out of. Anyway, there exist these in polynomials, right? Such that what? F of x is equal to q of x times g of x plus r of x, where what? R of x is equal to 0, or the degree of r is less than what? Right. Now look at this. This is in I, right? This is something in the ring of polynomials times g, which is by assumption in I, right? So this is also in I, because I is an ideal.
But should it be less than the degree of g?
Oh, yeah. Sorry about that. So consequently, r of x, which is equal to the difference of f of x and q of x times g of x, is in I, right? So what does that say about r? It's either 0. I mean, r is either 0 or it's got degree less than g, right?
It's not possible that because g is least degree.
Exactly. So r has to be 0, because otherwise it contradicts g having least degree. Right. And so therefore, f of x is what? Q of x times g of x, right? Which is an element of the principal ideal generated by g. So in other words, I is a subset of the principal ideal generated by g. How would you prove the other direction? Can you see why it is that the principal ideal generated by g should be a subset of I? Yeah, g is in I, so that follows immediately. Right. There we go. That proves that polynomials over a field form a principal ideal domain, because every ideal has to be principal. This proof also shows you how to find the generator for an ideal in a polynomial ring, right? You notice that this proof also gives us something else. This proof shows to find generator of ideal I, which is a subset of a polynomial ring over a field, we must find polynomial of least degree, right? That's sometimes a calculationally useful observation. All right, so moving along here. Definition. I think I've stated this definition before, but it bears stating again. And this is the definition of irreducible. D, an integral domain. All right. we say f in the polynomials over D, which, I'm sorry, I'm going to have to write f of x. It's too ingrained. You don't have to if you don't want to, but f of x and d of x, which is neither 0 nor a unit, neither 0 nor a unit, in d of x is irreducible if whenever f of x is equal to g of x, h of x, all right, with, of course, g of x and h of x in the polynomials over D, all right, then g of x or h of x is a unit in d of x. If a polynomial is not irreducible, it's said to be reducible. Now, we'll see there's another criteria you can apply to a polynomial, which is to say it's prime. All right? We'll get there later. But you may have been taught that prime and irreducible are the same thing. We make a distinction, though. These are technically different things in here. Just a warning, okay? And really, this is still not quite right. We should really say that f of x is irreducible over D in the case that this holds, because the context matters a lot. All right, let me give you an example of why context is so crucial here. So if we look at f of x equals to x squared plus 1, right? Is this irreducible? You should say, I don't know. You need to give me context, right? It's irreducible over the reals, right? But on the other hand, it's x plus I times x minus I. So it's reducible over the complexes. So where we consider x squared plus 1 to live matters a lot. Another example in this vein, if we look at f of x equal to x squared minus 7, well, certainly this is reducible over the reals, right? It's reducible over the complexes, but it's not reducible as a polynomial over the integers, right? If we look at this as an element of polynomials with integer coefficients, this is not reducible. This is an irreducible. See, because what you want to do, of course, is this, right? But you can't do that because the square root of 7 is not in there. One of my main goals today is to share with you a number of interesting results about how to judge irreducibility of polynomials with integer coefficients. All right? Yeah.
You don't have to say that it's reducible or irreducible over, like, R x.
No, I think R.
Does it make sense to say over R?
We don't really need the of x. The coefficients are the issue. Yeah. So another good example is this one. F of x equals to 2x plus 4 is irreducible over the rationals. And you'd say, well, what do you mean? Because I can factor a 2 out, right? But the thing is, if I factor 2 out, right? If I do that, that does not show reducibility over Q. Because 2 is a unit in the rationals, right? because a half is its inverse, and that's a rational number. But f of x, the same thing, you know, is reducible over the integers. See, because over the integers, that's 2 times x plus 2. And that's not a unit. This x squared plus 1 example, you can play with further. And so, check this out. If we look at f of x as an element of z3x, right? We can use the corollary I erased up here not long ago to see that it's irreducible. Try it out. So here I'm assuming f of x, of course, is x squared plus 1, right? So try it out. What's f of 0? 1. What's f of 1? It's 2. What's f of 2? Which is 2, right? So clearly, x squared plus 1 has no 0 in Z3, right? Consequently, f of x equals to x squared plus 1, irreducible over Z3. But on the other hand, if you look at x squared plus 1 as an element of Z5, right? You could look at that instead as x squared plus 1 is equal to x squared minus 4, which then tells you, pretty obviously, that that is x plus 2 times x minus 2. As you can see, that's a reduction, right? So x squared plus 1, is it irreducible? I don't know. Depends on the context, right? All right, so I now want to share with you guys a number of deep results on how to attack these kinds of examples systematically. The proofs are interesting, but not especially, they're not as interesting. Like, the reason I go through this slowly and somewhat carefully is because this is very much a potential test question, right? What is the logic here? You need to know the definition of principal ideal. You need to know what the division algorithm says. And there's not much more thinking past that. This is a very decent test question. In contrast, some of the proofs I'm about to show you would be malevolent test questions. Nevertheless, they are tools we'd like to use, and this is a 400 level math course, so we should talk about their proofs. But, you know, on the other hand, time is always an issue. So here we go. Now, some of these proofs I'm about to share with you, I could write out, and they would be reasonable test questions. I will let you be the judge of which ones those are. We can have a vote on each one. How about that? It's not binding, though. It's just for my amusement. Let's see here. Is it too soon to joke? I'm sorry. Yes. Come on. Ooh. Uh-oh. We're going to get advertised if I'm not careful here. Where was I? Let me get my laser. So first of all, and this is a really important one. So we got through, let's see here. That's not what's important. Oh, this, by the way, is an application of this remark over here. If you look at the mapping, this is just kind of an outlier to my discussion at the moment, but if you define the function phi that goes from real polynomials to complex numbers by value like that, and so this This is really a hybrid thing. This does not fit into our current. That's not the evaluation homomorphism, right? Unless I was to say that, well, anyway, it's technically not. But nevertheless, the kernel of phi is a principal ideal. And I'm not, we do this example later better, so let me just go on. Here we go. We stick with the plan. So here's the next thing down the list. Suppose f is a field and f of x has degree 2 or 3. If you have degree 2 or 3, all right, it's reducible if and only if it has a 0 over a field. And the proof is pretty simple. If it's reducible, then f of x has a factorization which includes a linear factor. Consequently, it has 0 by the corollary I just erased. On the other hand, if it has a 0, then we can factor it like that, and that's a reduction, right? Because this has degree 1 and that has degree 2, and this is not a unit because the units over the polynomials over a domain, certainly for a field, the units for polynomials over a field are just the units of the field. In other words, any non-zero scalar. That's the whole set of units for the polynomials, right? So here I'm in the context of polynomials over a field, so there you go. It's really nice. It's really nice. Be careful. That is for polynomials over a field. Right? Now, it breaks down at order 4. At order 4, you could have something like this. X to the 4th plus 14x squared plus 49. Well, that's x squared plus 7 squared, which shows you it's reducible. Take a 4th order. I factored into two things, neither of which are units, so it's reducible. There's a reduction of it. And yet it has no zeros. So that theorem's only good for order 2 and order 3. Don't be like me. Don't misapply the theorem I just stated on the previous page to order 4 and higher. It'll get you into trouble. All right. I don't think this term is in Nicholson. I didn't notice it, but the idea is in there. So I'm still working on combing through section 4.2 to come to terms with the distinction between my notes and Nicholson. But this much I can tell you. The content of a non-zero polynomial, what you do is you take the greatest common divisor of the coefficients. This is only for polynomials with integer coefficients, all right? So a number of the theorems I'm about to tell you are really just for polynomials with integer coefficients, all right? But for example, if your polynomial is monic, then the content is 1, all right? But more generally, if the content is 1, it's said to be a primitive polynomial. And so Gauss's lemma is down here. The product of two primitive polynomials is primitive. This example just kind of helps you get used to the idea. Here, I can factor out a 3, right? So you factor out a 3, and that leaves you with 3 times x plus 2. The thing that's left over is primitive. X plus 2 is primitive because the GCD of 1 and 2 is just 1. So if you factor out the common factor, all you're left with is relatively prime things, is the observation. So here's a proof. The product of two primitive polynomials is primitive. It's actually pretty simple to prove. You suppose you've got a pair of primitive polynomials such that the product is not primitive. Then if you take p as a prime divisor of the content, in other words, the GCD of the coefficients of the product, say it's p times h of x, and then you consider these polynomials with the reducing homomorphism, right? In other words, we take the coefficients and we map them mod p. That's that homomorphism I talked about last time. Then, well, with respect to the reduction homomorphism, we have 0 is equal to that because it's a multiple of p. But then we have this times this is 0. But the thing is, zpx is an integral domain. So I got a product of two things of 0 in an integral domain. Well, that means either that's 0 or that's 0, which is to say that either p divides that or p divides that, which contradicts those being primitive. So, all right. Exciting, I know. let's see here. So theorem, here's where it's actually interesting. Let f be a polynomial with integer coefficients, then f is reducible over q if it's reducible over z. So what this is saying is that you can judge reducibility of polynomials over q by just considering them as polynomials over z, which is super nice because polynomials over z, well, they're simpler to think about in some regard. But the proof basically, well, the proof is interesting in some sense. We take a monic polynomial in z, and suppose that we have h of x and g of x in rational polynomials such that f of x is their product. You take a as the least common multiple of the denominators, the coefficients, and b is the least common multiple of the denominators in g of x. So what that means then is if you multiply by the least common multiple of the denominator, what's that doing? It's clearing out the denominators in the h of x and the g of x so that a times h and b times g is a polynomial over z. All right. And then ab times f of x would be that, right? And so we can look at the content of these different polynomials. ch is the content of that, cg is the content of that. Then, so that means then we can also find primitive polynomials g1 and h1 such that bg is cg g1x. This is Gauss's lemma that you can always write any polynomial over the integers as its content times a primitive polynomial. So apply that 2 times, 1 here, 1 there, put it together, we get ab f of x is equal to this, is equal to that. And then so the thing is that this h1, g1 is the product of primitive polynomials, which is primitive, which means that the content of this is ch, gh, and so then I can realize that AB must be CHGH, and so if I divide this by AB or by CHGH, whatever you like, it gets f of x is equal to h1 times g1. And so we have f of x is equal to h1x g1 of x, where these are polynomials in z. In summary, for a monic polynomial in z, if you can reduce it like this for some h of x and g of x and q of x, then there exists h1 and g1 and z of x, which factors it. All right. If you're lost in this proof, let's look at the example. Here's an example of what's going on in the proof, okay? All the proof is this example. So if you have f of x is 6x squared plus 19x minus 7. Well, you can factor out the content, which here is, you can factor a 6 out, make it monic, let's say. That's the primitive. Well, anyway, I can factor a 6 out. Let me not say what it is. Then this is a rational polynomial, which is quadratic. You can factor it like so. All right? And then that factorization over q implies a corresponding factorization of the z polynomial by just multiplying the 6 back through, which gives you this. So we were able to reduce it in q, and then by unmultiplying the thing we factored out, we get back to a factorization in z. That's all the theorem's saying. You can play this game. But you can play it in general. That doesn't look especially interesting because, well, I would personally rather just do this from the outset, right? Like if you want to show that that reduces, isn't it easier just to factor? I mean, so the primary use of this theorem is more theoretical than practical, right? So in the interest of actually making good on that point, let us go on. The next theorem, and this one we use a lot, if we have p is prime and f of x is a polynomial with integer coefficients with a degree larger than 1, then you can reduce it mod p to get the corresponding polynomial with coefficients in z mod p, and the so-called reduced polynomial. And then the theorem says this is that if the reduced polynomial is irreducible over zp, and the degree of the reduced polynomial matches the degree of the original polynomial, then f of x is irreducible over q. And I know we don't have time for the proof right now. I actually want to spend the time on examples. But if you actually study the proof here, it involves I believe it involves the one we just went through, the interplay. But anyway, let me go on here. I want to show you the example. So for example, to decide whether or not 29x cubed plus 5x squared plus 2x plus 1 is irreducible as a polynomial over z, you can reduce mod 2. Well, mod 2, this is just x cubed plus x squared plus 1, right? And it's easy enough to plug in 0 and plug in 1 and see that neither of them are zeros. Consequently, you can't factor it, which means it's degree what? Degree 2, so it's irreducible. And since this is irreducible, and it also is what? Degree 3. Did I say 2? I meant 3. You notice that it's degree 3. The reduction is degree 3. The original one is degree 3. So by the theorem above, we get that this is irreducible over q. Here's another one. This one you can reduce over z2 to that. And that's not helpful, right? Because if you reduce mod 2, you get actually a reduction. So that doesn't help. That doesn't say that there's a reduction over q. It just says that the theorem doesn't apply here. So I look at mod 5. Mod 5, you get this reduction, and if you plug in 0, 1, 2, 3, and 4, you get all non-zero. Consequently, again, irreducible over q. So just like we looked at some of this idea before for looking for solutions to equations, right? Now I'm talking about factoring polynomials. That's the difference. This is one of your homework exercises. I warned you, this one is difficult. F of x equals x to the fourth plus 1. You can show that that the reduced polynomial is reducible in ZPX for any prime. So this pesky example is a counterexample to the method. It says reduction mod p doesn't always work. There are polynomials which escape its grasp. This example is technical, all right? Here, I try to look at this polynomial. What I do is I factor out a 35, which is nice. Then I've got this corresponding integer polynomial. I look at irreducibility, mod 2, I get this. All right? And if you look at that, it's got no 0, so it has no linear factors, right? But then you have to go looking for quadratic factors. How many quadratic factors are there to look for? Mod 2. You can make a list. What are the quadratic polynomials, mod 2? You've got your x squared plus 1, x squared plus x plus 1, x squared plus x. I think that might be it. I might have missed one, but you can make a finite list. And then to see if this is reducible, you just got to see if any of those actually divide this. How do you do that? Explicit calculation. So here I do it. Now some of those we can rule out because if they were there, they would have produced a 0 for the quartic. So it basically narrows the list down to this one, x squared plus x plus 1. And if you multiply this to get that, well, that forces you to have these equations, and they're inconsistent. So that shows you that, in fact, this quartic is irreducible. That was kind of a pain, wasn't it? I agree, that was a pain. Yes. That is why the following theorem is amazing. This is Eisenstein's criterion. In your textbook, it's stated in a nicer way. It's got point 1, point 2, point 3. I encourage you to look at Nicholson. Write that down for yourself. The way he says it, it's better. This is the same theorem, though. So if you have a polynomial with integer coefficients such that p does not divide, p is a prime, p does not divide the leading coefficient. However, p divides the rest of the coefficients. However, p squared does not divide the constant coefficient. Given all this data, those three things, that proves the polynomial is irreducible over Q. Given the work we just had to do in this previous example to show that the reduction, I mean, if you think about the previous method up to this point, this is way, way better if it works. For example, 13x to the 7th plus 2x to the 6th plus 4x cubed plus 18x plus 2. Look at the prime 2. 2 does not divide 13, but 2 divides this, 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 and that. 2 squared does not divide 2. So by Eisenstein's theorem, this is irreducible over the rationals. This is very nice. I will not prove Eisenstein's criterion just yet. So next time, I'll start by showing you one of the central applications of Eisenstein's theorem, which is that the cyclotomic polynomial is irreducible over Q. It's a straight, well, it's a little bit sneaky application of Eisenstein's criterion. So that's where we got to today. I will keep chipping away. By the way, if you look ahead, we will not get to the end of these notes. We will get to, I'll tell you where the end is as far as my notes go. Here, this is beyond the edge. So we will go through lecture 29 basically this semester, all right? In fact, all of this material will be on test 3. So